This lesson comes out of section 1.7, Infinite Series. First of all, just to recall the difference between a sequence and a series. A sequence is a list of numbers, so 2, 4, 8, 16, etc. 5, 10, 15, 20. Can be arithmetic, geometric, or any other strange list of numbers. We looked at something here called the Fibonacci sequence. And so these are all sequences. Any list, basically, is a sequence. If you start to add up those numbers, you have what's called a series. So if I said, what's 2 plus 4 plus 8 plus 16, and I could add up how many of those terms we wanted to, we would have ourselves a series. So a series includes the idea of a sum. You're adding something up. And so one thing I wanted to have a look at, maybe we'll do a review question like that first one I just wrote down. 2 plus 4 plus 8 plus 16, ... Let's do that as our first example. And we might be asked to find the sum of the first 20 terms. Well, I don't really want to write out 20 terms of this series. If I recall from Math 20 or 30, depending on which of the curriculum you used or went through, you have a formula that looks something like this to find this sum, or sometimes you'll see it written like this. And they both work exactly the same way, as long as you recall that A is always the first term of what you're adding up. The first term of in this case, it needs to be a geometric series, meaning it multiplies by some common ratio every time. R is that common ratio, whatever it's multiplying by, and N is your number of terms. And so if I do that, and I'll just use this last formula here, the sum of the first 20 terms should be 2, that's my first term, 1 minus 2 to the 20, because it just so happens that the common ratio here is also 2, divided by 1 minus 2. And so you have a bit of calculation required to find the answer, but you find it a lot faster than finding all 20 terms and adding them up by hand. And when I crunch those numbers, I get something like 2,097,150. Number itself not super important, but it's a gigantic number. And you can imagine that if I was asked the sum of the first 25 terms, 30 terms, 40 terms, this would just get bigger and bigger and bigger because I'm adding progressively larger numbers. Now let's look at something maybe a bit more interesting. Let's say I had 60 plus 30 plus 15 plus ... And I was asked once again to find the sum of, let's find the sum of the first 20 terms. So it's convenient. This time it's going to be the first term, which is 60, times 1 minus the common ratio. Now in this case the common ratio is a half. We're multiplying by a half every time, so 1/2 to the 20, and then divided by 1 minus a half. So let's figure out what that gives us. And when I put that in there, I got 119.9998856, lots of decimals, but 119.9999 would be good enough. 4 decimal places is probably way more than I need. In this case, something different is happening. And if I found, the sum of the first 40 terms, I'd be doing a very similar calculation, except I'd have 1/2 to the exponent 40 divided by 1 minus a half. And numbers in this series are getting smaller and smaller and smaller. In fact, incredibly small. So small that my calculator barely even notices they exist. So if I find this answer, even with a graphing calculator, if you're using one, 1/2 to the power of 40 is so small that when you say 1 minus that, the calculator just says it's 1. And so you're basically saying, what's 60 divided by 1/2, which is 120. Awfully close to what we already had. And in fact, it turns out that you can find what's called an infinite sum, the sum of infinitely many terms in this series, as long as your common ratio, if your common ratio is between -1 and 1, the infinite sum is equal to, and I'll call it S infinity, A over 1 minus R. Notice the reason why the formula up above changed was just that 1 minus R to the n term basically just becomes 1. R to the n becomes so small that R to the n, as n goes to infinity, R to the n approaches 0. So it becomes unnecessary to say 1 minus 0 times this. And in this example up above, we would get the exact same answer of 120 for the infinite sum of our geometric series, as long as the ratio is between -1 and +1.